Let's talk about the relative stability of cycloalkanes, cyclopropane, cyclobutane, and so forth. How do we measure stability? Well, one thing we can do to look at where the potential energies of these things are relative to each other is to burn them, right? So if we burn them and watch how much heat they give off, if something is sort of higher in energy, then it will give off more heat as it burns, as something with lower energy burns to the same thing. And so here, the only way, these are just multiples of CH2, so we can look at the heat of combustion per CH2 of these things to get some idea of relative stability. Okay? So if I do that experiment, and we did an experiment like this in chemistry 485, where it's called bomb calorimetry, a little steel container, you put a little bit of your stuff in there, pressurize it with oxygen, burn it, and see how much heat gets given off. And these are the numbers that come out there. You'll notice that per CH2, cyclohexane gives off the least amount of energy, and then it goes up in both directions as you go. If we just subtract through, we can kind of get a number called ring strain. And that's the idea that some of these molecules are kind of not happy being rings. Making a smaller ring or a larger ring than cyclohexane builds in this extra potential energy. So let's call that extra potential energy ring strain. Okay? And so we more or less define cyclohexane as having no ring strain. And then that ring strain per CH2, again, these are just these numbers divided or subtracted through. Ring strain goes up the further you get from C6. The total ring strain, you have to multiply back out. So what you can see is that, again, 0 for cyclohexane, a little bit for C5 and C7, and it's going to keep getting bigger the bigger rings you get. 3 is pretty bad. Notice that 4 is pretty bad, right? A 4-membered ring is almost as bad as a 3-membered ring. So it's not a gradual drop-off there. So, okay, let's dig into this. Again, this is all sort of experimental data. We see that, okay, as I burn this stuff, this is clearly lower in potential energy than the rest of them. So let's dig into why, starting with triangles. Why is cyclopropane higher in potential energy than the other cycloalkanes? So we can talk about ring strain as being mostly due to 2 different kinds of strain. The one is angle strain. So here's the idea. Carbon usually wants to have a 109.5 bond angle for sp3 carbon. This is 60 because it is a triangle, and that's how triangles work. And so how do we reconcile those 2 things? Well, the one way to think about it, not the only way, but one way to think about it is that my orbitals are still at that 109.5 angle, but because I've got 60 degrees here, my orbitals aren't directly overlapped anymore. The overlap is weaker. It's a little bit off center, right? So there's still a bond there, but it's quite a bit weaker than if the orbitals could really be pointing at each other. So smaller bond angle, weaker orbital overlap, higher potential energy compound, weaker bonds. So we can call that angle strain. The other part of ring strain is torsional strain. So remember, torsion is like the dihedral angle, right? So here we're looking at the dihedral angles between these hydrogens, and we notice that in that triangle, those hydrogens are forced to be eclipsed. They're stuck there. They can wiggle a little bit, but for the most part, they're kind of almost stuck, eclipsed like that. And that's going to, again, raise the potential energy due to electron-electron repulsion between those hydrogens. So again, if you are asked on homework, on a test, by a passerby on the street, why is cyclopropane so high in energy? You'd say, it's ring strain. Well, what is ring strain? Well, ring strain can kind of be broken up into 2 things, angle strain and torsional strain. Angle strain just says, well, the angle is too short, and so my orbital overlap is weak, and my bonds are weak. But the other half is that I have torsional strain because I've got hydrogens that are stuck eclipsed to each other, and so I'm suffering from that electron-electron repulsion as well. Here's cyclobutane. So cyclobutane because it's not stuck as a triangle, can actually pucker a little bit. You can see it's not all the way planar. And so our hydrogens are not forced to eclipse quite as badly. So there's a little bit less torsional strain than there is in cyclopropane. We can still see there is some angle strain here. These angles are not 109.5. They're not quite 90, but the angle strain, again, makes this quite a bit higher in energy than rings that are slightly larger, like cyclopentane. So here's cyclopentane. We talk about it in its envelope geometry. You can kind of see how 4 of these atoms are more or less in the plane, with one of them kind of going out. That envelope geometry does give it a little bit of torsional strain. Some of those H's kind of get close to each other, close to eclipsing each other. But this lets my bond angle get really close to 109.5. So my angle strain is quite a bit less, and so this is quite a bit lower in energy than the smaller rings. Finally, here's cyclohexane. So cyclohexane, remember, is that lowest energy ring. It's got my bond angles that are all 109.5, pretty much on the dot, and I've got no eclipsed hydrogens. So everything in this molecule is staggered, which again, nice. So this is why cyclohexane is so stable relative to all of the other cycloalkanes. It's got my bond angles at more or less perfectly 109.5, and I've got no torsional strain because I have no eclipsed hydrogens. How do I draw cyclohexane? So this is how I'm going to draw cyclohexane. I'm going to start with something like this. So I've got a line there, and I've got this a little bit offset V here. It's not quite a perfect V. It's a little bit off-center. Now this is the tricky part. Now I'm going to try to draw the rest of the ring parallel to these 3 bonds. So here comes this end. It's parallel to that end. Here's this one. It's roughly parallel to that. And here's this one, roughly parallel to that. So this is what your cyclohexane should look like. It can be tilted the other way. That's OK. It doesn't need to be perfect. But you notice how quickly I drew that? Yes, that is with decades of experience. But with practice, and you guys will get a lot of practice, you can try to draw these relatively quickly like that. So again, what makes a good cyclohexane is that my 3 sets of bonds are parallel to each other, a little bit canted to the side. Carbon takes 4 bonds. Let's put in the rest of the substituents into this thing. So I'm going to draw vertical lines going out of each of these carbons. The carbons that are already pointing up, this one, this one, this one, they get a vertical line going up. And the carbons that are already pointing down, they get a vertical line pointing down. And notice I'm trying to draw a little bit of perspective here. If I was really cool, I would make it consistent. Okay, so if you're obsessive about perspective, you can do this. Try not to draw MC Escher type things where I get the line breaks wrong. But in general, you can see this carbon is in front of that carbon. Also notice that when I'm drawing this chair cyclohexane, I'm not using wedges or dashes at all. My 3-dimensional drawing is going to come through regardless of that. So don't draw wedges and dashes when you draw these chair cyclohexanes. Each carbon is going to have 2 substituents, 2 bonds going out. One is going to be up, one is going to be down. So one is going to be axial, and one is going to be equatorial, like the equator. Okay? So notice that while this one is straight up and down, this one is kind of down and a little bit at an angle. It's actually parallel, right, to find more parallel to both of these bonds here. So like that. So here, up is axial and down is equatorial. Here, though, down is axial, so up is going to be equatorial. And this one is parallel to that bond and to that bond. Okay, again, it doesn't need to be perfect, but that's what it should look like. So again, each carbon has one axial substituent and one equatorial substituent. And each carbon has one up and one down, broadly speaking. However, up is not always axial. Axial can be up or down. Equatorial can be up or down. Let's put the rest of the equatorial substituents in. This one's got a down, it needs an up. This one's got an up, it needs a down. Notice that, again, I'm looking for parallel lines. Both of these lines are roughly parallel to these. Don't draw it going the wrong way. This one's got an up, so it needs a down. This one's got a down, it needs an up. So each ring has 6 axial substituents, as I've drawn here, and 6 equatorial substituents, and 6 up and 6 down. And you can kind of see that if I draw my creepy eye here, and I'm looking down this pipe, that these are going to be staggered to each other. And if I think about these hydrogens, they're almost like a gauche interaction. I can show that over here as well. Now, can I tell the difference between, say, axial hydrogens and equatorial hydrogens? Well, most of the time, no, because this compound can ring flip very quickly. So here, I'm going to show you an animation of it first, and then we'll go into detail. As you can see, I've got different color hydrogens to start with, and they are going to interconvert between being axial and being equatorial as it goes from one chair conformer to the other. Okay, so this chair ring flipping is pretty fast. So what's the potential energy surface look like? Let's take a look. So this is the potential energy surface for a cyclohexane ring flip. So ring flipping, relatively fast, about 100,000 times per second at room temperature. So that's fast enough where most of our analytical techniques can't tell the two things apart. And again, when you interconvert, everything that was axial will end up equatorial. Everything that was equatorial will end up axial. Okay, so in cyclohexane itself, that first barrier from the chair up to here, this is about 10.5 kilocalories per mole. The transition state looks like this. It's a half chair where you've got 5. It's essentially like the envelope for cyclopentane. You've got 5 atoms pretty much in a plane, and then the 1 atom still out of the plane. So quite a bit of hydrogen overlapping here, torsional strain. That's why that's so high. This can relax down to something called a boat. This boat is essentially just like it sounds, right? You've got these 4 carbons in a plane, and then you've got the 2 kind of ends up. But that boat actually isn't a minimum. The boat is a local maximum between 2 twist boats. The only difference is that we've taken that boat and, yes, twisted it in order to get rid of some of the torsional strain here. So if I twist it a little bit, now those hydrogens aren't eclipsing anymore, and I get a little bit lower in energy. So I go from the chair through the half chair, 2 twist boats connected by the true boat, and then back out the other way. So again, it looks like a big barrier here, but for the parent cyclohexane, again, it's a very, very fast process at room temperature.